Resonance stabilization of alkyl radicals. It can be explained by the concept of hyperconjugation. The stabilities of tertiary, secondary, primary alkyl radicals are explained by hyperconjugation. It is similar to that of explanation for stability of allyl radicals. Allyl radical is stabilized by overlap of two pieced orbitals of carbon atoms on the adjacent carbon atom on both the sides. That is responsible for the two different structures of allyl radical. But in alkyl radicals, this delocalization is possible through the overlap between p orbital occupied by odd electron and the sigma orbital of alkyl group. Through this overlap, the individual electrons can bind together three nuclei, that is 2 carbons and 1 hydrogen. So this type of delocalization involving sigma orbitals is called hyperconjugation. When we apply the hyperconjugation concept to explain the stability of ethyl radical is CH3CH2 radical. We know that ethyl radical it is a primary radical. Its stability can be explained by hyperconjugation. When we apply this hyperconjugation, we can see that ethyl radical is a hybrid of actually the first original structure, that is CH3CH2, and we can draw additionally 3 more structures. So when we analyze the structures of the additional structures, we can see that the double bond joins the 2 carbon atoms and the odd electron is held by a hydrogen atom. That means the odd electron occupied by the 2p-z orbital of the carbon atom can overlap with the sigma orbitals of any of the CH bond on the adjacent carbon atom. So as a result, the original CH bond has been broken and the odd electron is present on the hydrogen atom and a new double bond has been formed between the 2 carbon atoms. Similarly, we can draw 2 more structures because a CH3 group has 3 CH bonds. So any of these sigma bond, any of the sigma CH bonds can be broken and can be involved or can participate in the hyperconjugation. When we draw the hyperconjugation structures, we can see that in all the structures one bond is missing. So we can otherwise call this hyperconjugation concept as no bond concept or no bond resonance structures. So individually each of these no bond resonance structures, it is a different or a strange concept, and it may not contribute too much. If the contribution of each structure towards the stability of the alkyl radical may be less, but when taken together it adds to the stability of the alkyl radical. The CH bond is, as I mentioned, it is less than that of a single bond, and the carbon-carbon bond has a double bond character. And so as a result, the odd electron is partly accommodated by hydrogen atom. Contribution from these unstable structures, these hyperconjugation structures, if you take them individually, they are not that much stable. That's why it is said that contribution from these unstable structures is not that much important as for the resonance structures of allyl radical, because in case of allyl radical, both the contributed structures they are equivalent, and the resulting stabilization is large for allyl radical. But the contribution from this hyperconjugation structures of alkyl radical is not that much large, and we can say that ethyl radical is stabilized to the extent of 6 kilocalories relative to methyl radical. We know the bond dissociation energy for the formation of methyl radical it is 104, and for the formation of ethyl radical from ethane, formation of ethyl radical needs 98 kilocalories of energy. That means 6 kilocalories of energy is less than that of methyl radical. That much more stability is associated with the ethyl radical. So this is supported by this hyperconjugation concept. Due to this hyperconjugation, we can draw 3 more structures, and ethyl radical is a hybrid of 4 different structures. In case of isopropyl radical, we know it is a secondary radical, that is CH3, CH3. Point of attachment or the presence of odd electron is at the secondary carbon atom, that is at the middle carbon atom CH3, CH3. It is a result of 7 structures, 6 hyperconjugation structures and 1 original structure, that is CH3, CH3. As in the case of the previous example, ethyl radical, the methyl group can contribute 3 more structures. So in case of isopropyl radical, there are 2 methyl groups. Each methyl group contributes 3 structures. So total 6 hyperconjugation structures are possible for isopropyl radical. And what about tertiary butyl radical? Tertiary butyl radical, the structure is CH3, CH3, C. That is CH3 thrice C. That means on the carbon bearing the odd electron, 3 methyl groups are there. So as we know, each methyl group can contribute 3 more structures. So total 3 into 3, 9 hyperconjugation structures are there for tertiary butyl radical. So as the number of contributing structures increases, the stability of the hybrid will be more. So tertiary butyl radical will be more stable than secondary or primary radicals. So the larger number of the contributing structures means more extensive delocalization of odd electron and hence greater stabilization of radical. So bond dissociation energy of isopropyl hydrogen bond is 95 kilocalories per mole, and so the resonance energy of isopropyl radical with respect to methyl radical is 9 kilocalories. That means 104. That is 104 minus 95. 104 kilocalories is the bond dissociation energy of methyl radical, and 95 kilocalories is the bond dissociation energy of isopropyl radical. And in case of tertiary butyl radical, the bond dissociation energy is 92 kilocalories per mole. That means the resonance energy is 104 minus 92. 92, that is 12 kilocalories per mole. So out of this primary, secondary, tertiary, the tertiary is found to be more stable. So far we have discussed the stability of allyl radical as well as stability of alkyl radical. So stability of allyl radical is due to the capability of 2p-z orbital occupied by odd electron of each carbon atom to overlap with the 2p-z orbitals of carbon atoms on either side. So this contributes to the stability of allyl radicals, that is by applying theory of resonance. And in case of alkyl radicals, the stability is due to hyperconjugation, that is the tendency of the odd electron to overlap with the sigma electrons. Now we may be discussing the stability of allyl cation. Allyl cation is also a resonance hybrid of 2 contributing structures. Just like allyl radical, allyl cation is also a hybrid of 2 different structures. So look at the structures, structure 1 and 2. These 2 structures are actually equivalent structures. They differ only in the position of double bond as well as the positive charge. And the actual structure of allyl cation is a hybrid of structure 1 and 2. The allyl cation does not contain one carbon-carbon single bond or one carbon-carbon double bond. Rather, it contains 2 identical bonds, that is intermediate between single bond and a double bond. We can see by looking at the structure, we can see that there is a 1.5 bond. That means between the 2 carbon atoms, there is a full sigma bond and a half double bond between first and second carbon atom as well as second and third carbon atom. And the positive charge is not located on either terminal carbon atoms, but it is spread over both. Positive charge is spread over both the terminal carbon atoms. So in either of the contributing structures of allyl cation, there is a carbon atom with a positive charge. That means that particular carbon atom possesses a 2p-z orbital without electrons. So this empty 2p-z orbitals, it has the tendency to overlap with the pi electron clouds of the adjacent doubly bonded carbon atoms. So as a result, delocalization of pi electrons happens, and each of these two pi electrons, they helps to bond together all the 3 carbon nuclei. That means the carbon-carbon double bond is not localized or restricted between 2 carbon atoms, rather it is delocalized. This delocalization is possible due to the overlap of empty 2p orbital of the carbon atom with the pi electron cloud.